Hello folks, I recently prepared a video tutorial with the title of Modal Dynamics of an Axially Loaded Bar. Uh, what I would like to do in this video is repeat the same problem except that I will not be using modal dynamics. Instead, implicit dynamics will be used, implicit dynamics step. Now, let me remind you that modal dynamics applies only to linear problems. So if you have a problem that is not linear, or uh, perhaps you don't have an idea of how many modes you have to take, etc., you can probably use the implicit dynamics step more intelligently. Okay. Now, let me also remind you that there is also an explicit dynamics, which involves a great deal of impact and contact and nonlinearities, but you should have the license to it in order to be able to use that step. Now, for now, I'm going to concentrate on implicit dynamics, which covers a wide range of applications, including pretty much all structural dynamics problems. Okay, now, remember the purpose of these videos is to do simple problems, relatively simple problems, and show you the in and outs of 3D experience for that particular theme. Uh, And keep in mind that the FEA solver for native FEA solver for the 3D experience is the Abacus program, Abacus implicit program. Okay, so remember this is implicit dynamics model of the same problem above, and it is I'm gonna do this in the context of a one-dimensional element, in other words, a link element or a beam element, as you may want to refer to it. One end is clamped, the other end is subjected to a load f of t. The cross section, because we're using the link element, the cross section, the shape is not important. What is important is the actual area, which is 1 square inch. But I've drawn it as a square here, 1 inch by 1 inch. This beam is this link or beam is 200 inches long, but it's not drawn to scale. If this is 1 inch and 1 inch, this is not going to be 200, not drawn to scale. I'm using the Young's modulus of steel, 30 million psi. Poisson ratio, I'll take it to be 0, although that is not relevant because we're using beam element slash link element. Poisson ratio is not used. And the density that you see here in that weird unit is actually for steel. Okay, the loading that we're going to apply is going to be like so. So during that 0.001 second, or a tenth of a millisecond, actually this is during the 1 millisecond period, the load is ramped from 0 to 1,000, and then drop down to 0 during the same time interval. Now this will lead to a dynamic problem because the rise and fall is very small compared to the natural period of the structure. This is going to be a dynamic problem. Now, here is some information about the implicit dynamics in the 3D Experience online documentation. The important thing is right here. It uses the some version of the Newmark method, which is obviously unconditionally stable. Okay. All right. Now, what I've also done, shown you the result based on some of the selections that I have made here. And for example, the different initial time step, minimum time, maximum time, etc. And you've got to be careful on these choices. In other words, you can't just go ahead and recklessly choose some values and pretend that the results are going to be okay. You can see that depending on what you choose, you're going to think about this, make sure it makes sense, and the results may be different. Okay, so let's go ahead and create our model. It's a very simple geometric model. It's just a line which is bounded by 2 points. So let's go ahead and create 2 points first. One of them is global origin. The other one is 200 inches away on the y-axis. Okay. And now here are the 2 points that are created. I can create a line between these 2 points, between this point and that point. And if you want to see it, just make sure you fit it. The fit under view, there's the fit. Okay, so let me hide these 2 points because I don't want to put restraints inadvertently on these points. All right, we're going to create our material. So let's go ahead and to tools, create a material. I'm going to call this thing implicit dynamics video. Okay, and say okay. So it's going to be created in the database, but there is no, it's just a placeholder. There's no numbers in it yet. So right click apply, and I'm done with this window. I'm going to apply it to that part or physical product, and the check mark is applies it. So there we are. Let's put our numbers in there. Okay, so it's structural, general option. The general option, I can put the density, and the density in that weird unit 0.3073. Okay, and for stiffness, Young's modulus, you go to Abacus Multiphysics, mechanical, elasticity, elastic 30 million psi. So 30 and then 6 zeros. 1, 2, 3, 4, 5, 6. And Poisson ratio is 0. Okay, so let's save this. Now we're going to mesh it, and I'm going to use only 2 elements. Okay, the reason I do 2 elements is because the one that I did on modal dynamics also had 2 elements. There is no other reason. So let's go ahead to structural model, use MTFEM, and go to the mesh. Here is the beam mesh. So you click on it, you select that line, and you put the 100 inches here as the size, which means there's going to be 2 elements, each 100 inches long. Okay. The next thing I want to do the property of that bar or link. So we go to properties under this basically one-dimensional property. You say 1D link section. You select the support, and obviously the correct material is selected, and it's going to be 1 square inch, 1 inch square. Okay, and let me hide this green thingy here, which represents the properties. Now, as I did in the case of the modal dynamics, I'm going to create 2 manual groups. One group which is exactly this node in the middle, I'll call it the middle node, and one group which is the one at the end. If you want to plot the reaction force, for example, you need that, okay? And let me do that. So I'm going to go to groups, manual group. This is the first one, you see that right there? And I'm going to call it middle node, middle node. And let's do another one, which is this endpoint. And I'm going to call it wall node. All right, so we created our groups here, okay? And we're done. As far as the model is concerned, we're done. So now we're going to go to structural scenario creation. For the finite element model, we select the one that I just created right there. This is the one that I meshed, remember? Okay, so now we're going to go to procedure and scroll here to the right. This is static, right? This is the static RIX I have a video on that. I haven't done this yet. This is the one that we're going to be doing, implicit dynamics. The model dynamics is here, which is dimmed, okay? Because first you have to do a frequency step, and then you have to do model dynamics. But we are not going to do that. It's already done. So implicit dynamics is what you want to do, this guy. Click on it. Now, as I told you that I mean, you can't just recklessly go ahead and just do one problem and pretend that that's the answer. So I'm going to use 1,000 steps, first of all, 1,000 increment. And for the initial uh, maximum number of increment, 1,000, the initial time I'm going to use point 0, 1 e to the minus 4, 1 e to the minus 4, okay? And for the maximum, I use 1 e to the minus 6. And for the, the minimum, for the minimum time increment, I'm going to use 1 e to the minus 6. And for the maximum time increment, I will use 1 e to the minus 4, the thing that I started with. Now, you know, uh, the, this is the software automatically does the, uh, you know, time step adjustment, incrementation, okay? But if you, for example, say this is the minimum and that's the same thing as the maximum, then of course it's going to be using a constant step size. But here I will leave it to the software to start with this, never go below that, never go above this. And then we say, okay. Uh, Here, the nonlinear geometric effect is selected by default, and I didn't change it, although this is a linear problem. If you want, you can go and uncheck that. Let me remind you where it's done. Oops, under the implicit step, if you go to advanced, see that include geometric nonlinearity. But this problem is very, the loads are very low, therefore the deflections are going to be very small and going to be within the elastic range. Okay, good. So now we're going to do the restraints. Because I just want to do axial deformation of this is a link element, beam element doesn't bend. So I'm going to click on fix displacement on that line, and I'm going to fix it from moving in the X and Z direction. It can only move in the Y direction. Rotations are irrelevant because link elements do not have rotational degrees of freedom. Okay, so another one for that end to make sure that it doesn't fly away on the rigid body motion, cannot move in the direction X. Already we know that it doesn't, cannot move in the direction Y. Already we know it does not move in X and Z because it's on that line. And we say, okay. Now, as far as the load goes, we have this kind of a load. Therefore, we have to define an amplitude, okay? And I'm going to define my amplitude curve exactly like this. So I put a dummy load of 1 pound at the end of the bar. But that is a dummy load. It's going to be, basically multiplied by this, and it's going to give you the actual load. Okay, so let's go back there. First of all, to do the amplitude, you go to setup right there. You are in this scenario, so setup, and this is where you do tabular amplitude. You click on it. Make sure that this radio button is checked. Do not do this because if you check the total time and put your numbers in there and they're okay, there is no way you can change it from total time to step time, and that is going to cause a problem. They're going to give you error messages. You try to fix it. You see that you can't do that. You will have, in that case, you will have to delete that amplitude and do another one. So that's what I want. Step time is what I want. Now this has to do with the smoothing. I already mentioned in my other video that these are sharp corners. If you want to kind of make a fillet around here, smooth it out, then you do it like that. But I don't want it. I'll just make it 0. Let's put our numbers. For time of 0, displacement is 0. For time of 0.001, the load is 1,000 pounds. For 0.002, the load drops to 0. And then for the final time, 0.01, it stays 0, and it goes all the way to 0.001. Now, if you want to see whether you did this thing right or not, you put the cursor there, right click XY plot, and this is the curve that I generated. Okay, good. And we say OK. Now, we are done as far as pretty much the things that we wanted to do. So we go to simulate. Now, if I go and say, OK, simulate it for me, first of all, I'm going to start with a model and scenario check. You will see that it comes back with an error message saying that, hey, you did not specify what the output is. Let me show you. So when you do this, actually, let me, it, it may actually run, but I will not be able to plot the displacement of that point, of that node. So let's actually check it out. Let's check it out. Because it may run, but when you try to plot the uh, displacement of that middle node, I'm not sure if you can do that. We'll see. We'll see. We may make it lucky, and it's going to do it for us. Let's see. I'm pretty sure it's not going to work. We'll see. Okay, so because when we try to plot, get a history plot, you would not be able to see the displacement of that node. You see a bunch of things, but displacement is not one of them. Very simple problem. It does this very quickly. There's only 3 nodes in this model. Each node has only 1 degree of freedom. So very simple problem. And I have a feeling that, as I said, this is going to complete, but if you want to plot the displacement of that middle node as a function of time, we have not requested the, the, uh, the data, the output, and you won't give it to us. Yeah. By the way, if you click on that plot tab, you see that the progression is shown here through the entire time step. Oh, something failed, so let's see what the issue is. Okay, so close this. Let's look at the diagnostic viewer. Too many increments. Okay, yeah. So actually, let's go ahead and change our step time. Let's go ahead and to implicit dynamics. See for a second. Oh, this should be 0.01. Bad mistake. 0.01. I want to do the simulation over a 0.01 second. Okay. Okay. So let's run it now. So I made an error in specifying the total time. I didn't change it. It was 1. Default is 1. I left it at 1, and therefore, when it made the steps, I had a maximum of 1,000 specified. That's why it exceeded that and it stopped. Okay. Yeah. See, it finished this time. However, the question is, can we plot our graph? Okay, so it did. Let me close this. And in fact, yeah, it looks like, oh, this is the von Mises stress. If you look at the displacement, see, it's not giving us any value. So let's see what the issue is. Oh, yes. Another mistake. If you go to the load, if you go to the load, which was, where is this? Oh, even the load is not applied. I thought I applied it, but I forgot to do that. No problem. Standard. Right there. Calculate. I did not apply a load. So this is all correct. So load at that point, force 1 pound, but not the default amplitude. Default amplitude is a constant value. I want the one that I created, tabular amplitude. Okay, I forgot to put the load, and make sure that when you do that, you select the amplitude that you created. Now we're going to go simulate. Let's start with this model check. Then we do a simulation check. Everything that we got a few minutes ago was correct because there was no load specified, and therefore displacement was 0, and that's why I kept getting zeros in the model plot, not history plot, because I haven't done it yet. Okay, so this is done. Let's now run it. Here is the actual run. Simulate. It is kind of embarrassing because I created the amplitude, the tabular amplitude. I did not apply a load there, and these things happen very often to analysts and engineers and researchers and students. Very common. 3D Experience is an assistant that it gives you check marks for everything that you have done. So if you forgot to do the load, there won't be a green check mark uh, in that list. Okay, this is done. All right, very good. Now, let me close this. First of all, notice that this is a different. These are the displacement at different for the model at different times. So these are, you remember, to start with 0, and then for the entire model it shows up. But this is not what I want. I want to get the displacement of that middle node as a function of time. So this is what we have to do. Plot, history plot. You see that? History plot. Now, notice that it gives me some stuff, but notice that there is no displacement or reaction force. So it ran, and you can get stuff like this, but you cannot get the plot of, I don't know, displacement of the middle node as a function of time or reaction as a function of time. I already cautioned you that this may work, and it did work, but it's not going to give us what we want. So what we do is we go back to scenario. We go to the simulate. There it is. Simulate is already there. This guy is specifying the output. Click on it. So what I want is a history plot, first of all. I want to get the history plot of middle node group. Remember, based on groups. Groups. And it says you have two groups. Which one do you want? A middle node, right there. And then displacement, and then translation, and then we say OK. And it gives up at every step, every increment. Let's do another one. This time it's going to be, again, history plot, but based on group, but the wall node, and I want reaction force. And then we say OK. Good. Now we're going to run it. I don't have to do a model check because already it ran, so we know that there is no issue. There was nothing wrong with what we did. It worked. However, because we had not requested the output at the simulation stage, we were not able to plot something versus time. We could plot some stuff, but it was not translation. It was energy, or kinetic energy and things like that as a function of time for the entire model. That's not what we wanted. It's almost done. Okay, this part, of course, you have already seen. I haven't done anything differently. I didn't do anything changes here. Okay, so now we're going to go to plots, history plot. Now we're going to go expand this. Notice that there will be a translation here, right here, translation. Of course, because we selected that node as the group, it's going to be translation of that node. And it only moves in the y direction, so let's do a direction 2, and then we say apply, and there we are. This is that kind of a thing. Now I'll let you check with these other variations, see that you may get erroneous results. So some of these work, some of these give you erroneous results. But I also want to plot the reaction force at the wall. So let me say close this. Let's do another one, and then we say reaction force. It's going to be at the wall because that was defined for the wall node in the direction 3, 2, apply. There we are. And again, this makes sense because as time builds up, the load is pulling this thing to the right. Reaction force is going to be negative. Okay. And by the way, notice that these are roughly the same numbers that we got when I did modal dynamics. So we have solved this problem with modal dynamics, and in this tutorial we solved it with implicit dynamics. That is it.